You're standing beside a narrow creek in the Pacific Northwest, and the water is cold enough that your feet go numb within minutes of wading in. Fall is just starting, the maples are turning, and the air smells like wet leaves and something faintly rotten, drifting off the salmon carcasses tangled in the brush along the bank. Upstream and downstream of you, dozens more fish are doing the exact same thing at once. This whole creek turned into rush hour for something dying. Right in front of you is one salmon in particular, almost 3 feet long, fins shredded, skin peeling in patches, throwing everything it has left into pushing upstream against water barely deep enough to cover your calves. It just crossed roughly 2,000 miles of open ocean, and it hasn't eaten in weeks. Its whole digestive system has more or less shut down to save energy for swimming. No landmarks, no signs, and it didn't stop at any of the dozen creeks that looked, to you, basically identical to this one. It's headed for one exact stretch of gravel, in one exact creek, the same spot where it hatched years ago. The explanation most people have heard is that salmon smell their way home, tracking a scent trail all the way from the open ocean back to their birth stream. It's a tidy story. The problem is that for most of that journey, a smell simply can't travel that far. This is the story of an animal running 2 different navigation systems, and which one is doing the work changes depending on how close it is to home. Young salmon, still tiny fish called smolts, go through a physical transformation that prepares them to leave the river for the ocean. During that narrow window, their brain locks in the specific chemical fingerprint of the water they were born in. Dissolved amino acids leaching out of the soil, the vegetation, the whole watershed upstream. Every creek's chemistry is close to unique, like a signature. Not every species gets the same amount of time to learn it either. Sockeye often spend a year or 2 in a freshwater lake first, plenty of time to study the water, while pink and chum salmon head straight out to sea almost as soon as they hatch, meaning whatever they imprint on, they have to learn it fast. This isn't just theory. In field experiments around Lake Michigan, researchers raised young coho salmon on one of 2 distinct smelling chemicals for about 6 weeks, right during that transformation window, then released them into the lake. 18 months later, when the adults came back to spawn, the team metered those same 2 chemicals into 2 different creeks the fish had never actually been to. The fish sorted themselves by their artificial childhood scent, each one heading for whichever creek carried the smell it had been raised on. No real memory of a real stream, just a smell installed at the right moment, and that alone was enough to steer a 1.5 years later. The fish, in other words, can be lied to, and they'll follow the lie just as faithfully as the truth. Arthur Hasler was the zoologist who first proved this wasn't just a nice idea, back in 1954, by plugging the nostrils of one group of migrating salmon and releasing them at a fork in the river. The plugged fish picked their branch essentially at random. At that fork, no nose meant no usable map. So the smell system is real, but this is exactly where the tidy version starts to fall apart. A creek, no matter how chemically loud it is, can't diffuse out for thousands of miles across open ocean. Seawater dilutes everything past the point of usefulness. Drop a spoonful of dye in a bathtub, and the whole tub tints. Drop that same spoonful into a lake, and you'll never see it again. The ocean is that lake, scaled up past anything a nose could work with. If salmon were relying on smell alone out there, they'd be drifting across the Pacific waiting on a scent trail that essentially doesn't exist yet, while their energy reserves burn down day by day. So what gets it from the middle of the ocean back to the right stretch of coastline, before the nose has anything to work with? The answer is something the fish isn't smelling in any normal sense: Earth's magnetic field. Inside the heads of some salmon species, scientists have found tiny crystals of magnetite, a magnetic mineral, considered a leading candidate for a magnetic sense organ, essentially a compass built out of rock, embedded in living tissue. The leading hypothesis, developed by researchers Kenneth Lohmann and Nathan Putman, is that a young salmon records the magnetic field's angle and intensity right at the river mouth on its way out, a kind of coordinate, written in magnetism instead of latitude and longitude. The clearest evidence comes from a fisheries dataset spanning 56 years on the Fraser River in Canada. Sockeye salmon returning there have to detour around Vancouver Island, either north or south, 2 routes that differ by only a couple hundred miles. Which one they took wasn't random. It tracked with how far the magnetic field at each passage had drifted, that year, from the field back at the river mouth. In years when the field near the northern route matched the home signature more closely, more fish went north. Geomagnetic drift alone explained close to a quarter of the year-to-year variation in that choice, on its own, more than ocean currents could account for. By the time a salmon actually reaches the coast, that magnetic map has done almost everything it can do for it. The river is somewhere ahead, but now the fish is facing down dozens of mouths and inlets that all look nearly the same. This is where the baton gets passed to smell, except it isn't as clean a handoff as that image suggests. The two senses don't fully swap off. The magnetic sense just recedes as the chemical one takes over, both still running, one just mattering less by the mile. Back in the late 1970s, a Canadian research team poured a solution into a river diluted to a concentration that sounds almost fictional. 1 part human skin in 80 billion parts water. A few flakes, essentially, spread across a small reservoir. At that concentration, migrating salmon stopped in their tracks for a full half hour. The compound responsible was serine, an amino acid present in human skin, and, fittingly, adult men were the biggest smell polluters of the bunch. You didn't even need to touch the water. Washing your hands upstream was enough. So there are two systems here: a long-range magnetic sense that gets the fish into the right neighborhood, and a short-range chemical nose that finishes the job, loaded with a memory burned in back when the fish was barely old enough to swim, a coordinate written in magnetism, a signature written in dissolved amino acids, months of open water between the two, laid down before the fish had done anything else in its life worth remembering. But here's where the clean picture has some real cracks worth naming honestly. The ability isn't perfect. Tracking studies show that most, but not all, salmon return to the right home area, and the rate swings a lot by species and population. Some Atlantic salmon populations return at rates well below the numbers usually quoted for Pacific salmon. This isn't a guaranteed piece of hardware. Picture that same fish, years earlier, as a fingerling barely as long as your thumb, drifting downstream toward the ocean for the first time. Everything it's about to become capable of gets set up in this stretch, and it's also the stretch where humans have the most chances to quietly wreck it. Young Atlantic salmon that had to pass through a mile-long hydropower tunnel on their way to sea came back, as adults, with a noticeably lower chance of finding the correct stretch of river. The tunnel had severed the sequence of cues they were supposed to learn on the way out, cutting their odds of homing correctly by close to a fifth. Pollution does something similar from a different angle. In one study, just 4 days of exposure to a pesticide mixture, at concentrations matching real rivers in British Columbia, measurably dulled trout's response to natural odors. Two very different kinds of interference, same result. The map gets harder to read. The bigger fix to the story, though, is the two-step version itself. Nobody thinks the fish flips a switch from magnetic to chemical the instant it hits the coast, like a plane handing off from one air traffic controller to the next. Most researchers now describe it as a blend, with the brain weighing both signals continuously and the balance shifting gradually as the fish gets closer to shore. So the relay race image is useful, but it's a simplification, closer to two runners jogging side by side for a while, one slowly falling back as the other takes over, then a clean baton pass at a fixed line. The two-stage picture is still the easiest way to explain it. It's just not literally how the fish's brain runs it. Now go back to that creek. The salmon in front of you, battered, torn, close to dying from exhaustion, isn't thrashing around blindly. It ran a magnetic line across an ocean it can't see the edges of, then followed a chemical trace thinner than anything you could taste to arrive at this exact 10 feet of gravel and nowhere else on Earth. It's going to spawn right here, and then it's going to die. Not because it got lost, because for a salmon, arriving and stopping forever turn out to be the same event.